Hello, in this lecture we'll be studying the ideal gas equation. Okay, now first of all I'll give you an introduction. Okay. So let this be a container, let it be a balloon. I have a lot of molecules inside this. They're in random motion, right? So some go like this, and one goes like this, and one goes like this. So we have a lot of such molecules, right, in different directions, and they exert a pressure on the surface of this container, right? Now what is pressure? We know that pressure is equal to force by area, right? The force by area. Okay, so as the speed of the particles increase, as the velocity increases, the pressure increases, and as the velocity decreases, the pressure decreases. Okay, now you know what is this temperature. What is the difference between the temperature and energy? Temperature is actually the average energy of a particle, average energy of particles. So it is actually the energy per particle, energy per particle. That is what temperature is. Okay, per particle, the energy per particle, that is what a temperature is. It's actually average, so we take the average energy of different particles, and that is the temperature. Okay, now we'll be deriving, sort of deriving the ideal gas equation. I'll just do this. Ideal gas equation. Okay, now pressure. We have a pressure P. The pressure P is actually proportional to the temperature into the number of moles, or some number, let it be particle or mole or something. It's actually, so the temperature into the number will be the total energy, right? So the pressure will always be proportional to the total energy, right? Because as energy increases, the kinetic energy in these molecules increase, so they move faster. And as I told before, as pressure goes up, the velocity goes up, right? So the kinetic energy increases, so the pressure is actually proportional to the temperature into number of particles or number of moles. Okay, let it be a certain number of particles found in it. Now volume. We know that the equation for pressure is equal to force by area, right? So it's actually inversely proportional to the volume, right? Inversely proportional to the volume. Now in order to make this we need a proportionality constant to be multiplied, right? So let it be a proportionality constant R, any constant R into T into N divided by volume, right? Now we can write it as pressure into volume is equal to N into R into T, right? Now this is what is called the ideal gas equation. This is what is known as the ideal gas equation, where this P is equal to pressure, V is equal to volume, N is equal to, in most cases we actually take the number of moles. And when we consider different, for example, if I consider number of moles, the value of this constant R changes. if I consider particles or changes. We'll actually get into that, for a bit more. The T is equal to the temperature, right? Temperature. Okay, now this is the ideal gas equation. Now let me remove these. Okay. Oops. Okay, I just need this. Place it over here. The ideal gas equation. Now, is this equation applicable to all kinds of fluids or even solids? No, it's not actually applicable to them. Ideal gas equation is only applicable to ideal gases. Now, what is an ideal gas? Wait. Ideal gases. Now, what is this ideal gas? An ideal gas is a gas with molecules that do not attract or repel each other. Molecules that do not attract or repel each other. Now that is what an ideal gas is. Okay, now you got the equation, you know what is an ideal gas. There's not much something to know about this, just this R thing. Okay, we'll actually get into problems. Okay, now since I'm almost out of time, we'll do the problems in the next lecture. Okay, see you in the next one. Bye bye.